The next consequence we're going to look at is Morera's theorem, which is also a wild theorem. So if f is continuous in a simply connected domain, notice just continuous, not analytic, just continuous in a simply connected domain D, and if the value of the contour integral of f of z dz is 0 for all simple closed contours, C and D, then f is analytic. This is incredibly surprising, although maybe not surprising. So think about what happens with real numbers being continuous plus a condition. So it's not just continuous, but let's just pretend that it's just continuous for a second. Being continuous is telling me that I can differentiate to all orders. Now that, of course, is false for complex numbers as well, but continuous plus a contour integral condition will tell us that we actually can differentiate infinitely many times. Wild. Proof. Well, since the value of the contour integral is 0, f is independent of path. Right? Because if you could, I think we did this before, just to remind you though. If I had any two contours, say C1 and C2, then I can think about the contour, which is do C1, then do C2 in the opposite direction. So do C1, then do C2 in the opposite direction. I'm going to write that as C1 union negative C2. Well, on the one hand, that's 0. On the other hand, that's do C1, and then do C2 in the opposite direction. So we put a negative sign there. Oops. All right. So now what we can do is we can add that guy over. Oops, missed my circle there. Okay, so it's independent of path. All right, since it's independent of path, we can define an antiderivative. Oops, z dz. So this is an antiderivative. All right, so we have an antiderivative, and it's an antiderivative. So f prime exists and is equal to f throughout the simply connected domain D. Thus, capital F is analytic, and f is the derivative of an analytic function. Thus, f is analytic, as it's the derivative of an analytic function. Wild.